In this video, we will take up problem 3 of the sample midterm exam, and this problem is related to the power factor correction circuit. So the schematic of the boost based PFC is shown. The input voltage is sinusoidal voltage 150 volts peak, and the output voltage is also given. It is 200 volts DC, okay? And of course it satisfies the requirement of a boost converter that the output voltage is instantaneously higher than the peak of the input voltage. The switching frequency is as expected fairly high at 200 kilohertz. The load resistance is given. Inductor capacitor values are also given. So part A is to calculate derive an expression for the duty ratio, instantaneous duty ratio D of T for the single switch. Okay, so let's do that first. So this is a boost converter. So for any boost converter, the duty ratio, even for a DC-DC converter, so D of T is 1 minus the input voltage divided by the output voltage. So which in this case is 1 minus the input voltage is a sinusoidal quantity, and we need the absolute value of that because it's still a DC to DC converter. So it'll be 150 absolute value of sine of 377t, that's 60 hertz, divided by the output voltage, which is given as 200 volts. Okay. So that's the expected 1 minus sine wave expression for the duty ratio. 150 over 200 is 0.75 absolute value of sine 377t. Okay, that is the complete answer to part A. If you go back and look at part B, given the input side inductor is on the after rectification is 250 microhenry, and we need to calculate what is the maximum peak-to-peak ripple in this inductor current, which is also same as the high frequency ripple on the AC current as well. So this is a straightforward application of a formula. So we are in part B. The formula that we had similar to a boost was this delta I IL peak to peak is VO D 1 minus D TS over L, and we want the worst case. Worst case for a boost is when D equals 0.5. Okay, so substitute that D 0.5 over minus another 0.5, get 0.25, and in the notes it's actually written as VO TS over 4L, okay, because 0.5 times 0.5 is 0.25. That is written as this 1 over L. So that would come out to be 200 volts. TS corresponding to 200 kilohertz. Switching frequency is 5 microseconds divided by 4 times the L was believe it's 250 microhenry. Yes, 250 micro. Right. So that works out to be simply is 1 ampere. Okay, it's 1000 micro over 1000 micros, 1 ampere. So that is the answer to part B. If you look at the problem statement, part C is given the output capacitor value of 800 microfarad. We need to calculate the peak-to-peak voltage ripple in the output voltage, and specifically we want just the line twice the line frequency ripple, 120 hertz ripple. So we also had a formula for that. If you look at your notes, the formula for designing the output capacitor to limit the output voltage to a certain peak-to-peak value was this, and here we are given C0 and we need to calculate the VO ripple peak-to-peak. So VO peak-to-peak from that expression would be the output voltage, output power, sorry, P, divided by the output voltage omega, and then the C0. Okay. So then the question is, what is the output power? Output voltage is 200 volts. The output load resistance is 26.67 ohms. So PO is V squared over R, 200 squared over 26.67 ohms. Okay, so that power comes out to be 1500 watts. Okay. In fact, I chose the this odd value of output resistance to get this 1500 watts power. Okay, so P is 1500 divided by V out of 200 volts. Omega is this line frequency in radians per second, that's 377, times the output capacitance, which is given as 800 microfarad. 800 micro. Okay, so then calculate this equation. You would get C, let me see. I'm sorry, we are calculating the peak-to-peak ripple. So the peak-to-peak ripple comes out to be 24.86 volts, corresponding to this 800 microfarad capacitance. And as a check, you can see that this is somewhat close to about 10% of the nominal output voltage, 200 volts. So it's a reasonable value. If you get this peak to be like more than 200 volts, obviously that is a mistake. Or if you get that to be very low value, then that is also is probably not realistic. Okay, so that's part C. If you look at part D, let's see what we have. Part D is to write an expression for the instantaneous input current Is of t. Okay, so when we do this, we can neglect the switching frequency ripple and then just write the input current waveform. Okay. So in single phase AC circuits, the power P in, which is same as P out, which we calculated was 1500 watts. So that is equal to either Vrms times Irms. So this is for unity power factor, which is what we are considering, unity power factor. Okay. If not, there will be a cosine theta term. Okay. But for us, cosine theta is 1. So this is also equal to V peak times I peak over 2. Okay. Because the peak sinusoidal value is square root 2 times the RMS. So that's where this expression comes from. So V peak I peak over 2 is equal to 1500, and the I peak for the input current is 1500 times 2 over the peak input voltage, which is 150. So that is 20 amps peak current. Okay. So from that I can write the expression for Is instantaneous, Is of t, would be 20 amps peak value times sine same frequency of the voltage 377t, and in fact it is in phase with the voltage, so no further angle added. Okay. So it's 20 sine 377t amperes is the input current of this Is of t. Okay, so then the final part, which is part E, to draw 3 different waveforms, and these are required at the switching frequency detail, because the duration for which we're going to draw these waveforms is between 4 milliseconds to 4.01 millisecond, or a total duration of 10 microsecond. Okay, so our switching frequency is 200 kilohertz, or switching period of 5 microsecond. So we're going to draw 2 switching period waveforms for these 3 quantities. Okay, so the inductor current, the capacitor current, and the switch voltage. Okay, so the time over which we want the waveforms are between 4 millisecond and 4.01 millisecond. So I would get the value of d of t, the input current, at exactly at the midway point here. So so calculate d, is and so on at 4.005 millisecond, right in the middle of this waveform, of this duration. Okay, so d of t we already derived in the part A, I think, which was 1 minus 0.75 absolute value of sine of 377t. Okay, so in this substitute t equals 4.005 millisecond and then get the value of d. So d at t equals 4.005 millisecond comes out to be 0.2514. Okay. So that's one information we need to draw any waveform, the operating duty ratio. The second one, to draw the both the inductor current waveform as well as the capacitor current waveform, we need to know what is this input current, because the inductor current is really the input current but rectified. So Is of t at, again, t equals 4.005 millisecond. The expression for Is that we derived in a previous subsection was 20 amps peak sine 377t. Second, substitute t equals that 4.005 here. Once again, that comes out to be, in fact, okay, this is Is, but IL is really the absolute value of Is, because it's just going to rectify the Is. Okay, so Is at that duration comes out to be 19.96, so it's very close to the peak value. Okay, the 4.04005 is very near the 90 degrees point. Okay, so that's your inductor current inductor current value, or the cycle by cycle average value of the inductor current at t equals this 4.005 millisecond. Okay, so with this information, I think we are now in a position to draw the full waveform of IL in. In fact, you need another expression, the delta IL, peak to peak. Okay, now this is no longer a constant, unlike in the DC-DC converters. Here, the peak to peak ripple varies along the sine wave. So I have to say at t equals again 4.005 millisecond. The expression is same as before that we use, PO d 1 minus d ts over L. So in this, BO is 200, d we just calculated is 0.2514, 1 minus 0.2514, then 5 micro for ts, and L was 250 microhenry. Okay, so this peak to peak ripple at that instant comes out to be 0.75 amps peak to peak. Okay, so with these we can draw IL in waveform. It's going to be positive. Okay, so it's not this rectified sine anymore. It is at the switching frequency level, meaning we are zooming in fact near the peak value of that sine current over a very short interval of 10 microsecond. So okay, so this will be 4 milli, 4.005 milli, and this would be 4.01 millisecond time t. Okay, so inductor current, its average value is this Is average 19.96, and there are two cycles here. D is fairly low, 0.25, so it rises at a higher slope and falls, comes back to that value after one cycle, then rises again in the next cycle, comes back to roughly a similar value. Okay, that is your IL in waveform. The peak to peak ripple here is 0.75 with an average of 19.96. If you want to write out the values exactly, this peak is 20.335, which is nothing but the 19.96 plus 1/2 of the 0.75, and the lowest value here is 19.59. So that's the input inductor current waveform. The next one I will draw is the output capacitor current, again at the switching frequency detail. Okay, that's 2 cycles. This is the T on of the first cycle, T on of the second cycle. Okay, this is the capacitor current waveform. If you look at the capacitor here, when the switch is on, the diode is off. So the capacitor, there is no current coming from the input side. The capacitor current is simply negative I out. And what is I out? IO is 200 over 26.67. Okay, let me see what that value is. So 7.5 amperes. All right. So this IC of instantaneous waveform. So it's going to be a constant at minus 7.5 during the switch on interval, then jumps to a value equal to this drawn IL in inductor current waveform minus the load current. So when the switch is off, diode conducts and it conducts the inductor current. So IC in this direction coming down is IL minus the load current. So IL was 20.335 minus the load current of 7.5 is 12.84 here. Okay, then some slope here and back to minus 7.5 and then repeats. Okay, and this value here is 12.09. Okay, so unlike DC-DC converters, the average value of IC is not 0. That is the difference between DC-DC converters and either AC to DC, as in this case, or DC to AC converters. So IC is, we can write it out, minus 7.5 for a duration of 0.254 TS plus the average value of this is 12.465. So that's the average of 12.84 and 12.09, which is nothing but the inductor current 19.96 minus the 7.5. Okay. So that current lasts for a duration of 1 minus D, which is 1 minus 0.254 or 0.748 or 0.74. Okay, so this average IC bar, it's positive 7.45 amperes. Okay. So it is not 0, therefore the output voltage is not going to be maintained very constant. It is going to have this 120 Hertz ripple. That is, this current flowing through the capacitor increases the voltage during this period, and that is what results in that roughly 25 volts or so peak to peak ripple. Alright, so that is the capacitor current, and the last waveform to be drawn is that of the V switch. And this one is fairly easy to draw, assuming the output capacitor voltage is constant. So this is 4.005 millisecond, 4.01 millisecond, and 4 millisecond. Okay, so during the switch on period, the switch voltage of course is 0. Then it jumps to the supporting voltage, which is the output voltage, VO 200 volts for this entire off interval, then the next cycle, on interval voltage is 0, jumps to 200. Okay. Alright, so that's the waveform, and this interval here is okay, 4.001257 microsecond. There's nothing but 4 millisecond plus DTS. Okay, so that completes problem 3.